I welcome you all for the third lecture in the module 1. In the last class, we started discussion on controllable errors and we completed environmental effects or environmental errors. Now, today we will have discussion on remaining controllable errors. Now, we will discuss what is elastic deformation. Now, during measurement, sometimes what happens, the operator will apply more pressure on the moving element, so that the stylus or the jaw, moving jaw will compress the workpiece. So, due to this, what happens, the workpiece gets damaged and also the measuring instrument jaw or anvil gets damaged. So, we will get some errors in the measurement. So, how this can be eliminated? Now, we should have some sensing device to sense the pressure, applied pressure, for example, ratchet mechanism provided in the micrometer, or sometimes dial indicators are provided along with the instrument to sense the measuring pressure. And the overhangs in the setups should be minimized. If the part is overhanging, so because of its own weight, the measuring instrument may deflect or the setup may deflect, leading to some elastic deformation errors. Now, we should have some kind of adjustment for applying stylus pressure, which I have discussed. Sometimes what happens, the same measuring instrument may be used to measure different kinds of material like rubber, plastic and metallic parts. In that case, single pressure setting will not be enough. So, depending upon the pressure, the material that is to be measured, we need to set different settings, pressure settings. So, if we have such kind of adjustments in the measuring instrument, it will be always better. And then error due to deflection. Sometimes the workpieces would be very long and we need to support them using supports. Now, in such cases we have to use airy points. Now, you can see this diagram wherein we have a very lengthy workpiece, the length of the workpiece is L and it is supported at two places, two supports are there, the distance between the supports is D. Now, when we support the long workpiece at a distance of D, which is known as D, where D is equal to 0.577 times L, where L is the length of the workpiece, then even though there is deflection of the workpiece, the end faces will be parallel to each other, so that we can take the measurements by using end faces of the workpiece. If we support at any other distance, then ends will not be parallel, and when we use the end faces for the measurement, we will be getting some error. So, that we can show with the help of a simple diagram. I am writing a sketch. So, we have a long workpiece like this, and then it is supported using two supports like this, but the distance is not equal to 0.577 times L, where L is the length of the workpiece. So, in this case we can see that end faces are not parallel. So, when we use the end faces for measurement in such a situation, then there will be measurement errors due to the deflection of workpieces. And there is another kind of alignment error. Okay, this happens when the measuring instrument and desired dimensions are not properly aligned. So, this we can understand by using this by studying this diagram. We have the workpiece of some length, which for the length of this workpiece is to be measured. We have taken a scale for measuring the length. Now, scale is not properly aligned with the workpiece. Now, you can understand, we can see in the picture that there is a inclination of theta between the measured dimension and the edge of the scale. So, because of this we get a length of L, but actual distance will be L cos theta. So, this is known as cosine error. So, this we can eliminate by proper alignment of the measuring tool with the physical dimension that is to be measured. Now, so under controllable errors we have another error called parallax error. The definition of this we studied when we discussed about metrology terminologies. Now, this error occurs when the pointer on a scale is not observed along a line normal to the scale. Now, what is the remedy for this? So, we should always try to reduce the distance between the pointer and scale, so that this parallax error is minimized. Now, we should always use a base principle of alignment. That means, the axis of measurement and the instrument measurement should be always collinear, so that the error due to distortions are eliminated, and then error due to improper instrument selection. So, we can take the example of measurement of a very thin wire of say half millimeter diameter. Now, in order to measure this diameter, which is approximately 0.5 millimeter diameter, we should not select a micrometer having a range of 0 to 25 millimeter. If you select instrument having 0 to 25 millimeter, what happens is we are using the end portion of the range. So, wherein there will be error will be more. So, we should always, when we select the instrument, we should always use the middle portion of the range. Now, if you want to measure 0.5 millimeter diameter wire, it is always better we select an instrument having a range of maybe 0 to 3 millimeter or 0 to 5 millimeter if available, so that the errors are less. And then error may occur due to wear also. So, due to the continuous usage of measuring instruments, the measuring surfaces of the instruments are subjected to wear. For example, if we take vernier caliper, the faces of measuring jaws are subjected to wear. Similarly, the anvil face and spindle face of the micrometer, they are subjected to wear. Because of this, we get some error. Now, wherever possible, we should try to adjust the instrument so that so that the error is made 0. Otherwise, we have to calibrate the instruments, and then we should note down what is the error, and then when we present the measurement result, we should account for this measurement error. And many times the measuring instruments come with the tungsten carbide coated surfaces. For example, in the micrometer, anvil surface and spindle surface, they are tipped with carbide, so that the wear is less and the life of the instrument is more. So, that we can observe in this picture. This is the spindle. Now, you can see the tip of the spindle is the end of the spindle is tipped with a carbide tip. Now, let us discuss about non-controllable errors. So, these are beyond the control of operator, and what we need to do is we have to calibrate the instruments and we have to note down what is the error, and when we present the measurement data, we should account for the error. Otherwise, we should take a new measuring instrument wherein the non-controllable errors are very less. Or another remedy is we should calibrate the instruments, and then we should use such instruments. Now, first one is scale errors. Now, when we use some instrument, if the scale preparation of the instrument itself is wrong, then we always get the wrong reading. This is known as scale error. This can be eliminated only by calibration of that particular instrument. Now, we have another kind of non-controllable error which is known as reading error. This happens because of thickness of the graduation and the line spacing between two divisions. Now, we can study this picture wherein we have a long component whose length is to be measured. We are using a steel rule. Now, we can see the end of the workpiece is somewhere here. Now, if we read this scale, the reading is 128.8. The reading is between 128.8 and 128.9, but it is very close to 128.9. So, now what we can what operators will do, he will take a dimension of 128.9 plus or minus 0.1 centimeter. So, in this case that 0.1 centimeter becomes the reading error. Now, remedy for this is we should use instruments with digital display, or we should use magnifying lens so that we can approximate in a better way, so that reading errors are minimized. Now, we have linearity error. Okay. For a measuring system with linear output, the maximum deviation of the output of the measuring instrument from a specified straight line is known as linear error. Now, if you observe this picture, x axis is a true value of the physical quantity and y axis we have measured value, and we have a best fit straight line drawn using the end points. Now, other points are laying very close to that, and now this gap is known as error caused by non-linearity. So, this best fit line we can always draw by various methods, by using end points of the range, also by method of least squares to determine best fit line for all the values. Another method is using a method of least square to determine best fit line which passes through the 0 point. Now, the instrument which is having linearity error, we should know what is the amount of linearity error, and we should consider this while presenting the measurement data. The other kind of non-controllable error is hysteresis error. So, this is the difference in position between loading and unloading curves. Now, we can observe this picture wherein we have a loading curve, that means the measurement is done in the increasing order, and similarly in the descending order. Now, this difference is known as hysteresis. Now, how do we find whether there is hysteresis error? So, when the pointer does not return to 0 when the load has been removed, then it indicates that there is some hysteresis error. Now, the causes for this hysteresis error are many. This is maybe due to dry friction in the mating parts, moving parts. Because of the properties of elastic elements, also hysteresis error may happen. Also because of presence of internal stresses in the various components of the instruments. This can be reduced by proper heat treatment of various elements of the instrument, and also by proper stabilization of the various components of the measuring instrument. Then repeatability error. So, this is present in almost all measuring systems. Now, the figure shows the distribution of repeated measurements made on one part by one person using one tester. Now, I can understand that the different measuring points will fall like this, and we can always measure the mean of this. Okay. And now the gap between the mean line and true value is known as inaccuracy, and this gap will be known as repeatability error. So, this indicates there is certain inaccuracy in the measurement system, and the spread of the curve illustrates the degree of error due to repeatability. So, this can be eliminated by proper calibration of the instrument. Now, let us start the discussion on international unit system. There are many unit systems like imperial system, metric system, and this international unit system is an extension and refinement of the metric system, which is more convenient to use when compared to other systems. This provides one basic unit for each physical quantity which are mentioned below. For length, the unit is meter and the symbol used is m. Similarly, for mass, the unit is kilogram and symbol is kg. So, similarly, there are 7 basic units, and all of them have units and symbols as shown here. Now, coming to the measurement standards. Now, International Organization for Standardization is responsible for establishing the standards and maintaining the standards, and they will also responsible for calibrating the other secondary and tertiary standards by comparing those with the primary standards established by International Organization for Standardization with the help of its various technical committees. Now, there are different kinds of standards like material standard and wavelength standard. Now, under material standards we have line standard and end standard. Now, let us learn what is that line standard and end standard. Now, line is a fundamental physical quantity which plays a major role in our daily life as well as in trade and manufacturing system. The following types of line standards are established. The first one is imperial standard yard. So, this is a material having 1 inch square cross section, and it is made out of branch bar with composition of 82% copper, 13% tin and 5% zinc, and the bar is having certain length. Now, 2 gold plugs are inserted into the branch bar as shown in this figure on the neutral axis. Now, on the gold plug there are 3 lines are engraved. Now, the distance between the center line of left gold plug to the center line of right gold plug is taken as 1 yard. So, this is known as imperial standard yard, and this is kept at a temperature of 62° Fahrenheit. Now, there is another kind of line standard known as International Standard Prototype Meter. Again, this sketch shows a special cross section is used, and the length and breadth are 16 millimeters bar 16 millimeters, and this represents the neutral axis surface. This surface is at neutral axis, and 2 lines are engraved on this surface, and the distance between these two lines is taken as 1000 millimeter or 1 meter. Now, what is the material of this bar? It is made out of 90% platinum and 10% iridium, and this is kept at 0 degree centigrade and normal atmospheric pressure. Now, this is taken as 1 meter and it is used for comparing other measurement standards. Now, the second type of material standard is end standard. That means, we have a metallic bar, maybe of round shape or square shape, and the distance between end surfaces of the bar is taken as the standard. And these are more convenient to use when compared to line standard, and these are used in the workshop for practical measurements in workshop and in inspection laboratories. The examples are of the end standard are end bar and slip gauge. So, let us try to understand the end bar. These are used for measurement of large size of work. They consist of carbon steel round bars about 20 millimeter in diameter, and length is varying from 10 millimeter to 1200 millimeter. They are hardened at the ends up to 800 Vickers hardness, and whenever they are supported using Airy points, so that end surfaces will be always parallel. They are available in different accuracy grades like reference grade, calibration grade, inspection grade and workshop grade. Depending upon the usage, appropriate grades are selected. For example, for measurement in the workshop level, the workshop level grades are used. For calibration purpose, calibration grades of end bars are used. These end bars, they have threaded ends, so that the 2 or more number of end bars can be assembled to have required length. Now, second type of end bar or end standard is slip gauge. They are nothing but rectangular blocks of hardened and stabilized high grade steel or zirconium oxide. They have 9 millimeter wide and 30 to 35 millimeter long cross section. The length of the slip gauge is nothing but the dimension which it measures. They are hardened to resist wear, and they are stabilized to relieve internal stresses. They are made as per IS 2984 1981 and IS 2984 2003 standards. So, different grades of slip gauges are available, like AAA grade, wherein the very close tolerances are maintained, like plus or minus 0.05 micrometer. They are used to establish standards, and they are used for reference purpose. The second category is AA category or calibration grade, which uses medium tolerance on its length, that is plus 0.1 micrometer to minus 0.05 micrometer. They are used for calibrating the lower grade instruments, measuring instruments, and they can also be used for high precision gauging work. And then third grade is A grade or inspection grade, wherein wider tolerance is provided on the length of the slip gauge, like from 0.15 micrometer to minus 0.05 micrometer. They are used as tool room standards for setting other gauging tools. The fourth grade is workshop grade, or we say B grade, wherein the tolerance is wider, that is plus 0.25 microns to minus 0.15 microns. They are used as shop standards for precision measurement. Now, we have some photographs here. This shows the slip gauge set, wherein we have various slip gauges of different lengths, and then you can see the finish of the slip gauge. It is almost mirror finish. Lapping work will be carried out on the measuring surface, so that it will have very fine finish, and very close tolerances can be attained. So, this shows the slip gauge accessories, wherein we can have slip gauge holder. You can see the slip gauge holder here, and we can assemble the different slip gauges by ringing process. We can build the required length of the slip gauge, and we can put them in the slip gauge holder, and this distance can be used as the standard for the measurement purpose. Now, I am showing a slip gauge set. There are different grades of slip gauges are available, which we have already discussed, and normally we have two types of sets. One is a normal set and another one is a special set. In the normal set, starting from 1.001 to 100 millimeter, there will be totally 45 pieces. In the special set, starting from 1.001 to 100 millimeter, there will be totally 87 pieces. Now, I am showing a special type of slip gauge box. So, wherein we can see the slip gauges lengths, they are starting from 1.001 and they go up to 1.009 in steps of 0.001, and then starting from 1.01 to 1.49 up to 1.49 in steps of 0.01, we have 49 pieces, and then starting from 0.5 and up to 9.5, we have totally 19 pieces in steps of 0.5, and then starting from 10 and up to 100 millimeter in steps of 10, we have 10 pieces, and then we have we will be having two slip gauges. They are known as wear blocks. So, in this set they are missing. Now, I am showing one slip gauge of 80 millimeter length. This is the distance between two measuring surfaces, that means this surface and this surface. Distance between these two surfaces is 80 millimeter. You can have a look at the measuring surface. So, this is the measuring surface. So, this surface is finished ground, hardened, stabilized, and then lapped. We will have almost a mirror like finish. The flatness of the measuring surfaces will be a fraction of a micrometer. Parallelism between these two measuring surfaces is also very important, and it is maintained within a fraction of a micrometer. I showed a special type of slip gauge, wherein 14 millimeter slip gauge is not available. So, when we want 14 millimeter length slip gauge, we have to take two slip gauges and we have to build them. So, I have taken 9.5 millimeter slip gauge and 4.5 millimeter. When we combine them, we get 14 millimeter slip gauge. So, we have to combine the two slip gauges by a process called ringing process. I will just demonstrate the process. The two measuring surfaces should be cleaned properly to remove any dust and oily layer, and then we have to keep these two slip gauges like this perpendicular to each other, and we have to slowly move one slip gauge over other, and then we have to rotate like this. Now, you can see because of the molecular attraction between the two surfaces, there will be adhesion of the slip gauges. Now, the distance between this surface and this surface is 14 millimeter. While dismantling the slip gauges, we have to repeat the same procedure. We have to rotate the slip gauges like this, and then we have to slowly move, and then we have to remove it. So, this is a ringing process. So, like this, up to third decimal place we can build the slip gauges. Now, I am explaining the slip gauge accessories which are used along with the slip gauge set. Now, this is the slip gauge holder. We will be having slip gauge holders in different ranges. For example, the first one is having a range of 0 to 50 millimeter. Second one is having a range of 0 to 100 millimeter, and the third holder is having a range of 100 to 200 millimeter. Now, this is the base. You can see the bottom surface of the base. So, at the center it is relieved, and only here there will be contact with the surface plate, and we can observe that there is a screw here. So, now these two can be assembled using this screw and threaded portion like this, so that this assembly can be used as height master. Now, how to build the required height? Now, I have taken a 40 millimeter length slip gauge, and these are the measuring jaws. We can observe the measuring jaw surfaces. This is very finely finished lapped surface, and on the other side we have a curved surface. Again, this is lapped, so that both inner surface as well as outer surface can be used for measurement purpose. Now, I will just show the assembly. So, we have to assemble. Again, we have to ring the slip gauge with the measuring jaw. I showed the process of ringing. So, similarly, this should be ringed, and then assembly should be put into the holder. The assembly should be put into the holder like this, and then we have to tighten. Now, the distance between this surface and this surface is 40 millimeter. Now, this can be used as standard for measurement process. So, if required, we can fix this to the base. So, now this assembly can be used for both external measurement, that means we can measure external dimensions, as well as if we have a component with a bore. So, for it, this can be used for internal measurement also. So, from here to here it can be used for internal measurement. Now, this is a pair of measuring jaw with the dimension 2 millimeter. This is the inner surface, and this is the outer surface. The distance between the inner surface and the extreme point on the curved surface is 2 millimeter. So, this can be used for both internal measurement as well as external measurement. And then we have a scriber also. So, we can use this along with the slip gauge for scribing purpose. So, we have another kind of jaw which is having a center point here. This also can be used for scribing purpose. Now, what are the disadvantages of material standards? Sometimes accidentally if these standards are damaged, then it becomes difficult to remake them, particularly the imperial standard and international prototype meter. If they are damaged, it will be very difficult to re-establish them, and then very accurate lab conditions are to be maintained, so that there will not be any dimensional changes. In order to overcome these difficulties, wavelength standards are established. So, now meter is defined as the length of path travelled by light in vacuum in 1 upon 299792458 second. So, the light used to establish this wavelength standard is iodine helium neon laser at wavelength of 633 nanometer. Now, this is not affected by the environmental conditions. So, this is more convenient to use, and it can be established easily. Now, there are some subdivision of standards. Material standards are classified into 4 basic types. The first one is primary standard. This is a material standard which is preserved under very specifically created conditions like 20 °C. So, one example for this primary standard is international prototype meter. So, this cannot be used for direct application, it will be always used only for comparison with secondary measurement standards. Now, there are secondary standards. They are much like the primary standards with respect to design aspect, material aspect, and length aspect. These are compared with primary standards at regular intervals, and if there is any deviation, it is recorded. These standards are kept at various places in various countries for occasional comparison with tertiary standards. Now, what are tertiary standards? So, these are used for reference purposes in various laboratories and workshops. They are used for comparison at regular intervals with working standards. And now, working standards, these are physical standards, for example, gauge blocks. They are used for checking measuring instruments in the workshop. That means, workshop instruments are calibrated by using these working standards. These have traceable relationship to the secondary and primary standards by step comparison with higher level standards. Now, let us try to understand the meaning of calibration. Any manufacturing industry will have a goal of producing very good quality products. They want to supply zero defect products to the customers. So, the quality product should fulfill all the requirements of the customer for with respect to functions, with respect to size, with respect to looks, ergonomic aspect, etc., and they should have specified dimensions as given by the customer. So, in order to establish or have the specified dimensions, it is very necessary that measurement is to be carried out, and one should have good and accurate measuring instruments. Now, we discussed in the previous classes that due to continuous use, all the instruments are subjected to wear, and there will be certain amount of error due to wear. So, at regular intervals, the workshop instruments should be compared with the equipment placed in the standards room of the plant, and then the amount of error should be noted down, and if possible one should try to eliminate or minimize the error due to wear by making some adjustment. This process is known as calibration. In order to carry out calibration as per set standards, a number of calibration laboratories are established at different levels. like the in-house calibration lab, which is also known as standards room in a manufacturing plant, and then we have professional calibration labs established by measurement experts, and then at the higher level, at national level, we have national physical laboratories. Now, in-house calibration lab, this is set up within a company for calibrating its own workshop measuring instruments. Very specialized and sophisticated equipments are placed in the calibration lab, and the workshop instruments are occasionally calibrated using these sophisticated instruments. Now, what are the functions of calibration or standards room? It should have a temperature of 20°C, which is as per international standard, and they should calibrate the various workshop level instruments at regular intervals or as and when needed, and it should check the various inspection gauges, plug gauges, etc., and should also maintain very delicate equipment available in the plant in good condition. Now, the calibration intervals for different instruments are shown here. The vernier calipers, height gauges, micrometers, dial gauges, they are normally calibrated every 12 months. Once in 12 months they are calibrated, and similarly slip gauges and distal dial gauges, they are calibrated once in 3 years, and radius masters are calibrated once in 24 months. This is only an example. So, like this, each instrument will have its own calibration interval. Now, higher level compared to standards room is professional calibration labs. The very experienced people and measurement experts, they establish these calibration labs and they run the calibration labs. They maintain very good quality, accurate and precise measuring instruments, sophisticated instruments in the professional calibration labs, and these are used to calibrate the equipment of the manufacturing plants. And these professional labs should get accredited by National Accreditation Board for Testing and Calibration Lab as per NABL norms. In-house calibration lab need not have this accreditation. Now, examples of NABL accredited labs in India, the Central Manufacturing Technology Institute situated at Bengaluru, Fluid Control Research Institute established at Palakkad, and then Central Mechanical Engineering Research Institute at Durgapur. So, these are some of the NABL accredited labs in India. Now, let us see what are the calibration facilities available at Mechanical Engineering Research Institute. They have calibration facility like coordinate measuring machine, CNC coordinate measuring machine, ML10 gold standard laser, and then laser align meter, internal diameter measuring machines, perthometers, universal profile projectors. So, like this they have different kinds of facilities for calibration purpose. And following types of instruments and gauges can be calibrated at Mechanical Engineering Research Institute. The instruments like micrometers with setting pieces, vernier calipers, height gauges, depth gauges and height masters, dial gauges of different kind, straight edges, slip gauges, all these types of instruments can be calibrated by using the facility available at Mechanical Engineering Research Institute. Now, at the highest level in India, we have National Physical laboratory which is situated in New Delhi. So, this is the Measurement Standards Laboratory of India. All the professional calibration labs instruments are calibrated at NPL at regular intervals, and they get NABL certification. Now, some of the facilities available at NPL are shown here. They have length measuring machine with laser interferometer. They have Flick standard calibration with 60 nanometer measurement uncertainty for in-house traceability of roundness through laser interferometer, and they have 1000 millimeter length measuring machine, Zygo interferometer for flatness measurement, and then 3D coordinate measuring machine, and then they also have gauge block interferometer. Apart from this, they have other sophisticated instruments for the purpose of calibration. Now, in this session we discussed about the various kinds of errors, measurement errors, and then we also studied about international unit system and various measurement standards like line standard, end standard and wavelength standard, and what are the levels of standards like primary standard, secondary standard, tertiary standard and workshop level standards. And then we tried to understand what is the meaning of calibration and how it is carried out, and what are the various NABL accredited labs available in India, and what facilities they have for calibration purpose. So, these things we understood in this lecture. Now, we will stop the lecture. Thank you.